Welcome, ladies and gentlemen, mathematicians. I am going to talk a little bit about types of numbers and some of the notation that we have for it. And this may have to break up into two different parts, and I'm hoping that we can get it all done in one, but if we can't, I may need to do two different videos here. So I'm going to start with the numbers that we use all the time and we think of as being little kid numbers. I'm going to talk about natural numbers, sometimes called counting numbers. Counting numbers. And this is really like 1, 2, 3, and so on. And little kids are, if you ask a little kid to count, this is how they're going to count. So this is kind of why we call it the natural or counting numbers. And we use, the notation on this is we use a fancy schmancy N. And this isn't the best drawing of it, but there we go. So here is my natural and counting numbers. And this is going to wind up being almost like the rings of a tree. So that we have everything that is inside one becomes encapsulated into the next one in most cases. I won't say every case, but most cases. So then we have the whole numbers. Which is our natural numbers plus 0. And that's it. Whole numbers are only positive. They are, the natural numbers are counting numbers plus the 0. All right, so now we're going to talk about integers. Which is the plus and minus of the natural numbers plus 0. All right, so we've got all the positives, 1, 2, 3, 4, 5, and so on. And then we've got all of the negatives, -1, -2, -3, -4, -5. And then we have the 0. And so hopefully this is making sense. If not, obviously get in touch with me and we'll figure out how to explain it in a way that makes more sense to you. Now, because it was the Germans who came up with this particular notation, we have a fancy schmancy Z. And that's for the word Zahlen, which is, I believe, German for number. And at least that's what I've been told. I don't speak German, so I can't attest to that 100%, but that's what I've been told. So our integers are, it's called Zahlen, that's why we have a fancy Z. We have our natural numbers, we have the opposites of our natural numbers, which is the negatives of those, and we've got our 0. So, the next one is rational. And this one's a little tricky. It can be written as a ratio, and it can be written as a ratio or a terminating decimal, and or a repeating constant, like 1/3 becomes 0.33333 forever. That would be the case of a non-terminating decimal that is considered rational. So it's or continuous. So it's got a continuous decimal with a pattern. Alright, so this is kind of a mess, but you kind of get the idea. Alright, so if we've got something that's rational, then chances are pretty good we've also got something that is irrational. And I'm going to create another new whiteboard for this. So irrational, oops, irrational. God, it helps if I turn the pen on, doesn't it? Alright. So let's go with it. Irrational. Yep. My pen occasionally goes a little crazy. So that's irrational. And it kind of makes, it's kind of funny that my pen went crazy on irrational. But an irrational would be a case of a number that never has a repeating pattern. And it goes on forever. One of the most famous examples of it is pi. We use pi. We call it 3.14, right? It's approximately equal to 3.14. But if you were to take a look at it, they've actually taken it out to several million decimal places. And so far, no one has been able to find a pattern or a repeating, something that repeats. So it goes on forever and ever and ever, right? So, and there's no rhyme or reason what number is going to be next. Another one would be anytime we have a number under the square root that is not a perfect square. So if I have a 2 under here, I'm going to have 1.4142 something blah 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 forever. Doesn't repeat, doesn't end, goes on forever. So because there's no pattern, and it looks like there is, but there's not actually, so I would need to generally go out another couple decimal places. But because there's no repeating pattern to work with, we are not able to like write it completely as a fraction. So our 3.14, I know some people say 22 over 7, you know, that's another one that's approximately equal to, and that's great, except that it isn't the exact number. It's not exactly pi. So if you can't write it completely as a fraction, then you're facing something that is an irrational number, because rationals can always be written as a they can always be written in the form of a fraction, and it would be a complete fraction. So let me go back to, I'm going to go back to this one. So I'm going to change this one up a little bit. I'm going to put irrational kind of off to the side, and I'm going to put it in a different color so that it's clear that we are not talking about the same group. So irrational. And this is its own little beast, right? It's its own little thing. It's not part of this mess here. We are not using these numbers and this in this at all, okay? So let's go back. I'm going to change back to my purple, of course, me and my purple. And we're going to talk about real numbers. And we have a fancy schmancy R for reals. All right, that's our real number. Maybe I should rewrite that a little less big so that it's easier to see. So that's our real number symbol. And that's basically all of our irrational and rational. So this is kind of everything. And we will talk about complex numbers. I'm not going to throw that at you right yet, but there is another layer to this that's called complex numbers that incorporates all of the real numbers and all of the imaginary numbers, and I'm going to just leave it at that.